Alright, so this is my biweekly update for May 27, 2022. Hopefully it should be pretty brief, and I will go more in depth regarding its contents and a few other things in our meeting on Monday. So most of my focus has been on the revisions of the COVID manuscript. Um, Aside from the other issues I addressed in the previous update, and the one we discussed in our previous individual meeting. And now I've been focusing on an actual section that referee 4 actually requested that we add, namely the one that deals with the protein ligand interaction analysis. So I looked at a handful of lead candidates, namely the ones that passed the drug likeness screening with one or fewer violations. And I opened the complexes up in Pymol, and I looked at the interactions they had with their individual protein structures. The only interactions that appeared were polar contacts, and I presume all of which were hydrogen bonds. I actually checked by looking at the atoms, and yeah, all of them were hydrogen bonds. None of them had any pi-pi interactions, which I found interesting. And some of them had as few as one interaction labeled, and some had as many as 5 or 6. So quite a disparity, although I did notice a general rough trend of the more interactions that appeared in Pymol when I ran a command, which I'll show on the next slide, the stronger the binding energy and Rosetta energy units. So, essentially with this little section that he requested we include, I don't really know if I can draw too many inferences. I don't feel like I would be comfortable doing that based on the limited data we have, except simply stating that um, the lead candidates, both in terms of binding affinity and drug likeness, had certain interactions with their proteins, and these were their interactions. And I would showcase that in a figure, which I'm going to make in Pymol, and then just describe what they are. I can't really go into more depth regarding, because they have these interactions, then this means this. I can't really make any inference beyond that, and I haven't really seen other papers go into more depth other than simply stating what the interactions were. I don't think he wants us to go into depth regarding that either. Um, and I also noticed that, our drug likeness section is technically complete, but it could be beefed up a little, particularly in regard to the toxicity prediction. I haven't found a server that also looks at promiscuity other than SwissAdme, but if I will, I intend to cross-check the results between found by SwissAdme and those found by the second promiscuity server, because 2 molecules I'm kind of concerned about, and I will go into that when I discuss the interactions on the following slides. Okay, so the command I used was show sticks by res, all within 5 angstroms of ligand. I found this on a YouTube tutorial. And I can also label them. Obviously, these won't be the finalized figures, but these are the interactions I obtained. And I will make a zip file of all of the interactions I currently have. I'm still waiting on 2 that I don't have, but Ray is going to send me the PDBs because he did the dockings of those structures, and I'll look at the interactions of those compounds. But 3,3-dimethyl quercetin was one of the leads that passed the drug likeness screening as well, with 1 or fewer violations. And it formed a total of 6 interactions with 6W9Q or NSP9, all hydrogen bonds. Some of the molecules had clashes. I didn't include them here, but maybe I should discuss them. I don't know. I made note of them, but I didn't include them in any of the pictures I have yet. Another example, 10-methoxycamptothecin, another lead that passed the drug likeness screening, formed only one polar contact with a residue in 6YHU, which is NSP7 and 8. And despite only forming one contact, it was a lead. It had a decent binding score. And amentoflavone was one of the molecules that was promiscuous based on our data, but Swiss ADME didn't reveal it to be promiscuous at all. It didn't have any pains violations, which is what indicates potentially promiscuous molecules. Um, but it was a hit against 8 out of the 15 protein structures we screened, along with another one that I'll talk on the next slide. And this molecule formed a total of 10 or 11 polar contacts with 6VWW. And I haven't looked at other structures of that it was a hit against, but I'm going to ask Ray for them because he has them. And I'm going to see if, I mean, it seems logical that the structure is capable of forming many hydrogen bonds because of the tons of oxygens it has around the aromatic rings. It also has a bunch of hydroxyl groups on this other end. So it's really capable of forming hydrogen bonding interactions, and I mean, that might explain why it lends itself to being a frequent hitter. But it wasn't identified as such in Swiss ADME, so maybe that's why I was thinking of finding a complementary screening to it in order to, I guess, bolster the promiscuity analysis. And similarly to amentoflavone, it seems to be a problem with the flavones. I don't know, I've read that somewhere. Agathis flavone also has 7 or 8 polar contacts with 6VWW. I presume it has similarly many polar contacts with other molecules because it's very similar in structure to amentoflavone, forms a similar number of hydrogen bonds, and it had hits against 7 of the 15. And these two molecules also happen to have the lowest binding energy score of any molecule, -20 Rosetta energy units. So yeah, I'm I don't know. I'll look into these further, and if we have time, maybe we can discuss them a little in right after the drug likeness section. Maybe a blurb will suffice. But other than that, what I intend to do with these figures, I've watched a YouTube tutorial that shows how you can move the labels in Pymol, the labels of the residues, you can move them above them, and then you can either render them a little further to make them more appealing and leave the figures as is, or you can make sort of a 2D representation of the ligand and the residues with which it interacts, a more simplified 2D schema. I still don't know what to do. That's actually one of my questions later on, how I should represent this graphically as a figure. And another cool thing I found was a surface map. So you present the protein as a surface, and you color the residues that the ligand has polar contacts with in a certain color, and those that it has nonpolar contacts with in a different color, and then you color the rest of the protein. This was actually done in figure 1, I believe, if I can pull it up. With the area where yes, as so. Essentially like in figure 1 where the red highlights are, that's what I was thinking of doing. And then I was thinking of describing the residues verbally in the description. So that's what I'm conceptualizing, but please offer me any suggestions for making the interaction figure better. I mean, this is also what I've seen. I haven't seen this so much in other papers, but I've seen simple diagrams of Pymol or chimera outputs. Okay, so my abstract was accepted to ACS Fall 2022 for the in-person poster session. Yeah, that was nice. This was in the computers and chemistry session. I didn't feel like it would because none of the topics really felt like they fit with the COVID project, but apparently they deemed otherwise. That's nice. Another analysis I did. So referee 4 mentioned towards the middle of his suggestions that certain proteins have incomplete regions. Um, and he mentioned the case of 7K3N NSP1. And initially I didn't know how I could find those, but then I looked at the PDB sequence and I found exactly how those uncertain regions are denoted in the sequence, namely by dashes. And I looked through all of the other structures we screened, and I found that two other protein structures, namely the spike we screened and one of the helicases, have one or more of such uncertain regions. And while in the case of NSP1, the uncertain region is on the complete opposite end of the protein of the area actually sampled by the ligand, in the case of the helicase and the spike, one of the uncertain regions is actually really close to one of the ligand placing coordinates obtained from Cas-P. So the ligand was the area in that area, the area around that coordinate was sampled in the docking protocol. So I guess I don't know. I'm leaning towards just admitting this. I mean, I don't really know if I can argue against their suggestion that we take a look into this and whether we should or shouldn't be concerned about this result. I'm just thinking about admitting that this is the case for the spike and the helicase. For the helicase, I can go into specifics and say that one of the coordinates sampled in the Rosetta docking protocol was near one of these uncertain regions. And in the spike, something like two of the coordinates were near the uncertain regions. But I guess I can just simply mention that as a shortcoming. I don't really think there's a way to argue around it, really. Interestingly, though, if I can pull up Pymol, there is Pymol actually. So 6VWW NSP13 was in the PDB file. It didn't show any uncertainties. However, when I fetch it, it gives me these grayed out residues, which are not actually located on the structure. These are different from the uncertain regions in that there's no dashes, but I don't know what this sequence here is referring to, the sequence of grayed out residues. So I made a note of all the ones that had grayed out residues in case they were uncertainties. But the peculiar thing about this is when I actually download the PDB structure and I open it up in Pymol, this is downloaded from the PDB, the grayed out residues don't exist. So this is a complete PDB structure, no apparent uncertainties. But when I fetch it in Pymol, the uncertainties appear, so I can fetch it. There's probably an easy explanation to that. See, no uncertainties for this one. And the uncertainties should appear for that one, grayed out residues. And such is the case for a few others. Actually, a lot of the other protein structures. I guess I should look into this. I haven't found anything yet. But yeah, that was really the caper of the uncertain regions. My thought is we should just admit that this is a shortcoming of existing RCSB data, and that any future docking works should look to find the latest, highest resolution protein structures. And those should always inform the most recent docking results, the most up-to-date protein structures. So I'm going to meet with Ray and Joel in the near future to make a final master document, if you will, combining the edits I made for like all the minor typographical things which are thankfully the overwhelming majority of the other suggestions made by reviewer 4. And we're just going to come to an agreement on those, as well as the points raised in the previous writing club meeting by the group regarding better wording of sentences, incorporating citations. All of those will be put into sort of a final document, which we will share. And then, I guess, per the editor's instructions, we're going to prepare an answer sheet for the reviewers showing how we addressed the points they raised and where we did so. I'm still focusing on glycandoc and affinity maturation, more in tandem with this going forward, because the revisions hopefully will near their completion towards the end of, I don't know, 2 weeks from now at the most. And these, I think I'll solicit some help on the coding end of things to automate this. I have a good idea of what I want to do, but to automate them, I will probably stumble and struggle, so I'll solicit some help. I don't know if they would be available. I know Ray's busy with the manuscript, but I'll ask him if he has time to help me automate the glycandoc for all of the top 100 homology modeled structures obtained through AlphaFold of the chimeras and of the grafts. So I should have all those structures once I run them through AlphaFold. And then also automating the affinity maturation protocol, automating the residue selection process. So once the ligand is docked via glycandoc in a specific site and refined in that site, residues within X angstroms of the docking site will automatically be selected for each individual protein ligand complex, and those will be the residues mutated in affinity maturation. And I'm not automating the selection of the number of rounds now, not yet. For now, it's just going to be set at 3 rounds of affinity maturation. Maybe it will be tailored to each individual case, but I don't know what to base that off of. So to explain this more clearly, I'll bring this old flowchart back, showing the plan of attack for glycandoc affinity maturation going forward. So once all of the homology models are obtained from AlphaFold, presumably after this, stability optimization will be done, or either after this or prior to this. I don't know if actual protein structures are needed or if just the sequence is needed. If just the sequence is needed, then that will go into AlphaFold first, and that will already be optimized for stability. Obviously, MYC is removed. I took care of that with the chimera grafts I did, and MYC is gone. I'm not using it from the plasmid sequence. Then all of them will be relaxed into Rosetta force field. This is just I have a Slurm file that just relaxes them. I just need to have it apply to all of the AlphaFold PDB files. This actually takes about 15 minutes, but if I run them in tandem and I manage to run all of the structures in tandem, they should all take 15 minutes combined. Then protein ligand docking, standard docking protocol. Maybe the score function will change. Ref 2015, that's the most up-to-date one. But since it's not a small molecule, but that's a consideration that I don't really have backed up by anything. Then the best scoring complex for each structure will be selected. We have a script that selects the best 10. All we need to do is change the 10 in that script to a 1, and the best scoring complex will be selected. This one will be refined with glycandoc. The ligand will be perturbed a little in order to find a better configuration, given that glycandoc has optimized weights for carbohydrates. Of those, 1,000 or so models will be made, since glycandoc will only sample 1 coordinate. The best glycan dock pose will then, of each protein ligand complex obtained, will then be uh, transferred to the Rosetta into the design of ligand binding sites protocol. This is one step that I will need help automating. Selecting X number of residues within the protein ligand interface to mutate and to make a res file with them. Ray is pretty good at this, given that he has template files. He's made template files for other necessary docking input files that we used in the past, XML files and such. And if we have a template for a res file, we can just make a script that fills it in as needed based on certain conditions. So he's done this in the past. Not for res files, but for XML files, for options files, and other files that need filling in for docking. Then using those res files, which is really all we need, the design will be conducted 3 times initially. So optimal sequences will be found by the end of 1 round of design. The best scoring sequences will then be transitioned to another round of design, and then another. And then I still need to figure out the logistics of running this 3 times. Initially, I'll just run it once, and then I have run it once on a toy model, but not on any large number of protein ligand complexes, which will actually be the case. And the model I ran it on wasn't even GD2. It was something I downloaded from the PDB. And then I'll select the binding energy threshold. I hope to make it not arbitrary because that likely doesn't look good. And then those sequences will be extracted. And the input structures that will go into all of this will be all of the chimeras and all of the grafts that we have. So many modeled structures along with GD2, which we already have. Okay, so questions. So what suggestions do you have for how I should go about making the interaction figures? Because I have the data. I know how to label the residues individually, but I want to make it look somewhat aesthetically pleasing, and I have an idea of how I would like to do it, given the protein surface diagram and coloring the residues, as I showed with what Ray did in Figure 1. I like that idea, but maybe something would look better. And to what extent would computational work, like what I'm mentioning I'm doing, be included in the antibody methods chapter, or will it be more yeast surface display and expression, which seems like the intent of that particular methods book. And that's about all.